volume, I don't have much control, no? I really don't have any control for the volume part, only my speaker.
Yes, sir. Nim speaker super ಜಾಸ್ತಿ ಮಾಡ್ಕೊಂಡು ಸಾಕು.
Let me see. Does it work now?
ಈಗ ಪರವಾಗಿಲ್ಲ ಸರ್.
Okay. I will
It's
do
better,
that.
sir.
Okay, no problem. Yeah. All right. So just one second. Okay. So the topic is distributed graph analytics, and Professor Srinivas said, how am I, I am an expert in compiler design. That is correct. So the way the connection with graph analytics began is when we started exploring the, how to program graph analytics algorithms in existing programming languages. And thereby there were lots of difficulties which led us to a PhD thesis. The last bullet shows that Falcon, a domain-specific language for graph processing. So that's exactly how my connection with graph analytics began, maybe 7-8 years ago. So today we will explore, a little bit of graph analytics. I am not going to concentrate on the compiler part because I understand that this is not a compiler specific lecture. I don't want it to be. I will give you examples of graph analytics, where they are used, and one example of fraud detection, special features of distributed graph analytics, and a domain specific language for graph processing. This is going to be our agenda for the lecture. Okay. So now, what exactly is graph analytics? See, we have a lot of data available in the form of a graph. We store, manage, and query data in the form of a graph in general. So a graph in general is just a mathematical object in some sense, with vertices and edges. But when the semantics of real life are added to it, then I will give you show some examples. So for example, a social network graph, it has a lot of what are known as nodes, which are dots in this picture. All these are the nodes of the graph, and these are all the edges, and there is a high density in the middle. This is how social network graphs, which show relationship between people. The relationship is the edge, the nodes are the people. So that's how we use graphs in practice. Here is one more example. This is all picked from the doing some sort of a flood risk famous Twitter graph. So the nodes are the people and the edges are the follow relationships, as we all know. So these graphs are extraordinarily large graphs. I will a little more of that will be, I will cover that a little later. But believe me, they have millions of nodes and billions of edges. That's how the sizes are. And this is the reason why graph processing is not going to be a trivial matter. And it's usually not possible to do it in a very simple way on single processor machines. What is graph analytics? So this is the usage of graph algorithms to determine the relationships and the overall structural characteristics of the graph. So more of this as we go on. And it is not as if graph analytics actually was brought into, which was not born today. There are lots of applications of graph analytics in compiler optimization, optimizing supply and distributed chains, and power and grid analysis, computational geometry, etc. These are all existing applications. What is special about today? Why is it becoming very important? Today, our very well-known applications such as Instagram, Spotify, LinkedIn, these are all actually graph analytics applications. They are relationship and connection-driven applications based on graph analytics. Social network analysis is a big buzzword. And what is its use? Its use is in business improvements. So, for example, identifying what the known as network influencers. Who are network influencers? A simple example in our real life, there are leaders. They may be political leaders, they may be industrial leaders, they may be academic leaders, whatever. So these people influence the society around us. Therefore, it's important, you can even abstract the notion of a network influencer and then identify network influencers in a huge social network graph and use it for various purposes. A classic example is the research on the famous Panama Papers. So, in fact, the journalists were the ones who used graph analytics to uncover politicians, their shell companies, and the hidden wealth. This was a couple of years ago. So that's exactly one of, a very large application. The second possible application is detecting fraudulent transactions. I will give you an example in more detail somewhere in the middle of the lecture. Then finding another simple example, finding optimal location of new public services for maximum accessibility. I will tell you how it is going to be done. Something that I cannot elaborate on are molecular simulations and disease identification. So how do diseases spread, especially the endemics? Of course, the COVID is something we don't even understand well, but there are very well-known diseases such as cholera, typhoid, and many smallpox, and so on. And these were actually, very difficult to control. So research has been done on how they, disease actually is identified, how it spreads, and all that. So graph analytics is used in such applications. Then we all know that whenever we log into something, it will throw you some suggestions like people you may know, songs you may like, restaurants which are nearby you, ... All these use graph analytics to identify similar users and enable personalized recommendations. That's how the usage is. So let me cover very basic methods of graph analytics. So graph analytics, let me again summarize. They're all about analyzing graphs for information. Okay. So what types of analysis are possible on graphs? One is known as centrality analysis. Another one is known as community detection. Third one is connectivity analysis. And fourth is path analysis. All these have practical application. And those are the applications I am going to cite now. Okay. So let us begin with the centrality analysis. What is centrality analysis? Basically, it says how important a node is for the connectivity of the network. So, for example, if you take the popularity of a product, right? How do you gauge how popular the product is? That can be done from the number of tweets related to the product. But then there are also fake bots which are launched by the competitors to bias such data. So it may actually launch a lot of tweets trying to promote their own product. How do you detect such fake bots is an application of centrality analysis. So it uses a centrality known as degree centrality. Let me show you an example of this and then we will go further. There is a very nice book from O'Reilly. If you just search for graph analytics and O'Reilly, you will get that, and it's a freely downloadable book. No problem about that. So here is a very small extract from a Twitter graph. So, and this software called Neo4j also tells you how to visualize graphs. So after applying what is known as the degree centrality algorithm, a graph, is shown, visualized in this fashion. What is degree centrality? So take this large node, for example. Why is it very large compared to this or this? It is large because the in degree of this particular node is actually the highest in the entire graph. So there are edges which are incoming. These are all incoming edges. So 5 of them. This has 4. This has 5. This has 1, etc., etc., etc. So it kind of visualizes in some way. So degree centrality is related to the in degree and out degree of the node. So it basically tells you what is needed here. If the in degree of a particular, for a product, if the number of tweets which is related to the out degree is very large, and if there are a large number of follows which is related to the in degree is very large, then people will say, okay, so many people are following this product, the tweet of this product, therefore it must be a very popular product. So this can be kind of assessed based on degree centrality. The second important application is, how do you find an optimal location for a new public service for maximum accessibility? A very simple example is our mobile phone towers. Where exactly should it be located in a public place? So this is computed using what is known as closeness centrality. What is closeness centrality? This is again a very simple quantity which can be computed from a graph. It says which of the nodes is closest on the average to many other nodes. So for example, this node and this node are closest to many other nodes on the average compared to, for example, this or this. That's easy to see. This is connected to a large number of nodes, whereas this is connected to only one node, etc., etc. So closeness centrality can be computed by computing the shortest distances between pairs of nodes. And there is a very celebrated algorithm which is well known to a lot of people, the Floyd's all pairs shortest path algorithm, that computes pairs of shortest paths, shortest paths between pairs of nodes. So using that information of shortest paths, a metric called closeness centrality can be computed, and that brings us to the question of how to find optimal locations. So this is not very far from any node in the system. That's the idea of optimal location. So if there are lots of houses, they are all going to be the nodes. So it is not going to be very far from any one of these houses. So that is the optimal location. Then this I already talked about, but I will give a lot more information on this in a few minutes. How do you find individuals who influence the flow around a system? So that can be computed using what is known as betweenness centrality. I will come to that. Let me finish this slide instead of going back and forth too many times. Then improving the drug targeting by finding control genes for specific diseases also has an application is an application of betweenness centrality. Then how do you find very influential features for extraction in machine learning? And that uses a measure called PageRank. I will tell you a little bit about that also. And finally, ranking text for entity relevance, that is, which is the semantically most relevant entity in a text, in a paragraph, and that is related to natural language processing, and that is also related to the centrality measure of PageRank. So in other words, when we do centrality analysis, we may compute degree centrality, we may compute closeness centrality, there are many others. We may compute betweenness centrality, we may compute PageRank centrality, and there are a few others also, which are not exactly very important to us today. So using these measures, one will be able to actually analyze the graph for certain properties. So that is graph analytics. So let me now show you a little more about betweenness centrality. So for example, for every pair of vertices in an undirected graph, that means there are no arrows on the graphs, there may be many shortest paths between two nodes U and V. Yeah, this is something well we know. For example, take this graph from Wikipedia. If I want to go from here to here, there will be many shortest paths. Absolutely no problem. So the betweenness centrality BC is the vertex between betweenness centrality of a vertex V is the number of shortest paths that pass through V. Okay, so let's see what it is here. So let us say this is my node, this is my node, and here is, for example, this node or this node, etc., etc. So let us say we compute shortest paths from between every pair of nodes, right? So between this, between this, and so on and so forth. You can see that between this blue, very dark blue node, it kind of it is very central to the graph, in the sense a large number of these shortest paths pass through this particular dark blue node. Similarly, this light blue node, for example, is also very important, but a relatively lesser number of shortest paths pass through this set of a node. And if we go on like that, this light green is even less important, and eventually this orange even less important, because very few shortest paths between pairs of nodes pass through it. But the ones on the periphery, the red ones, are the least important, because very small number of shortest paths between any two pairs of nodes pass through these red node, this. So this formula is not very important, but the definition is very important, because it tells you the number of shortest paths that pass through V. That's very important for us. And what does it tell you? Vertices with a high betweenness centrality may control information passing between others, because they lie on the largest number of paths taken by the messages. Their removal from the network will disrupt communications to the maximum extent possible. So this is the importance of betweenness centrality. So if this is removed, a lot of disruption in the network may happen if this is the message network. Whereas if I remove this, not much may get altered. And such central nodes also indicate the influencers. For example, if you consider this node corresponds to a leader, either political or industry or academic, it's a different matter. If this person is taken away from the scene, then a lot of people around him will not know what to do, because they would have been going to that person for advice. Now the person is not there anymore. So that's exactly the role of a social influencer, network influencer. And which particular node has maximum influence can be computed, can be determined by computing this betweenness centrality. That is the importance of this centrality measure. Okay. So same example, these are the most important as far as betweenness centrality is concerned. All others are weaker in that sense. Now, what exactly is this PageRank? I mentioned a couple of applications for PageRank. So let's go back a little bit and recall them. Finding the most influential features for extraction in ML and ranking text. These are the two applications that I mentioned for PageRank. But let us first understand what is PageRank. How does it say these are the most influential things, etc., etc.? And how was PageRank born? PageRank actually is a contribution from Google. And PageRank, how did it actually take birth? It was actually born to when Google wanted to determine the most important websites. When we search for something, Google lists a lot of websites from the top. They are actually ranked in some way because they are, one of them appears number 1, the second one appears number 2, etc., etc. So this is exactly why Google started with this research on PageRank, ranking web pages. And it works by counting the number and quality of links to a website or web page to determine a rough estimate of how important the website is. So importance of website was the goal when Google began this research way back in 90s on PageRank. And now it is a celebrated PageRank algorithm. A very large number of research papers and theses have come out on the PageRank itself. And nobody knows exactly which algorithm Google uses for page ranking because it's a proprietary information to PageRank. This algorithm was released to the public quite some time ago, and people have done research on it. So let us see what PageRank is, and with a very simple example. So there is a graph underlying the PageRank algorithm. The vertices in the graph are the websites accessed by the user. Very simple. And an edge A to B represents the outgoing URLs from website A to website B. That's all. So, and the page rank of a vertex is high when it has more incoming edges. So these are the basic things about a page rank algorithm. So let's see what exactly it is. I am not going to write a program here, but PageRank A, the website A, in the graph, it is a vertex. First, let us consider this part. So there are many items here, PRT1 by CT1, PRT2 by CT2, and finally PRTN by CTN, which are all added. So this T1, T2, etc., right? These are all the pages which have URLs linking to A. Okay. A is the page for which we want to compute the page rank. So in other words, here is a node. There are lots of incoming nodes here, incoming edges here, right? So these are websites again, which when we go to B or C or D and click a link, it will take us to A. That is the basic idea. Okay. So PRA is the page rank of A, and N is the total number of web pages. PRT1 to PRTN are the page ranks of the pages which have URLs linking to A, incoming edges to A. And then we have CT1 to CTN. These are the out degrees of vertices T1 to Tn. That's very important. And what do they represent? they represent the number of links on the sites T1 to Tn respectively. So there may be a lot of links, but all of them may not go to A. Some of them will go to A, some of them will not go to A. We are now considering only the out degree of vertices, all of them together. We are not bothered about whether they go to A or some other node. The reason is we want to find out a fraction of those will go to A. That's already captured in this. Okay. Then there is a parameter called D, which is the damping factor. What is the damping factor? It is the probability that at each page, a random surfer will get bored and jump out of the page. And this is very high. Okay. All of us, when we go to a page, very quickly get out of that page. We don't really stay on that page for a long time. So people get bored very quickly is indicated by 0.85. This is again something that we don't have to worry too much about. That's required for some other purpose. Okay. So let's see what happens here. There are 4 nodes, 4 web pages with this sort of connection. From B, there is a link to A. From B, there is a link to C also. From D, there is a link to A, B, and C. But there is no way you can get to D itself. There is no way you can get to D. So that's important here. So how do we compute PageRank? Initially, all page ranks are just assigned 1 by n. N is the total number of nodes in the system. So 0.25, 0.25, 0.25, and 0.25. Now, B has 2 edges going out, right? So the way we look at it, 0.25 is divided by 2 and half of it is transferred to C, and the other half is transferred to A. So B has an out degree of 2 and hence transfers 0.125 to A and C each. What about C? C has only out degree of 1. So the only way of getting out of C is to jump to A. And therefore, the whole of 0.25 is transferred to A. D has an out degree of 3. So only 1/3 of the time we go to A. So the transfer is 0.083 to A, B, and C each, 0.25 by 3. And the page rank of A is the sum of these 3. So this is how we compute the page rank after one iteration. If there is something which changes, then page rank is computed again and again. That is how the page rank is computed. And variants of this are used in machine learning, in natural language processing, etc., etc. So computing page rank seems to be a fairly simple job, but you must keep in mind that there are millions and billions of edges and nodes in the system. Okay, so when you look at the graph that Google creates, it will visit the websites all over the world in all servers, collect information, build this graph, compute the page rank, and then give you a result. All this happens on their Google processor farms, clusters. Okay, again, a simple example on the same graph that I took. I will skip that. So that was about centrality. Now, there is another measure called, rather another item that we need to find out. How do you detect communities in a network? So it is possible that there are many of these, like that, small groups of nodes which are kind of connected, but within the graph, there is a large number of connections. There are a large number of connections within the small clusters here. So the basic idea is to detect such clusters. This is called community detection. Clustering nodes based on distance and based on density, how many nodes are in that system, in that cluster. So why is it very useful? Estimating group stability. and detecting what is known as small world behavior. So this uses what is known as a triangle counting algorithm. And what we are doing is to detect clusters like this. These are all the clusters that we have. Second application, making product recommendations based on a group affiliation. What does this group use? Does it use Colgate or does it use Close-Up? That sort of a recommendation goes out from the group. It's very beneficial. Well, this happens in every organization as well, right? So instead of a single individual making a decision, it's always more powerful to make a committee give out a decision. So this is based on strongly connected component algorithm. Then understanding consensus in social communities. So maybe voting patterns, which cluster votes for which politician. This is based on what is known as a label propagation algorithm. And I'm going to talk a little more about this fraud ring, how to detect fraud rings. I'll not talk about it now. Okay. So very briefly, if you have a graph of this kind, A, B, C, D, E, F are all nodes and edges here. When you talk about a strongly connected component, for example, A, D, and E, finally B, C, and F, they are the two strongly connected components in this graph G1. There is a path from A to D to E to D, D to A, right? A, D, E, A is a cycle, but it is not always necessary to be a cycle in a very large graph. It could be a connection through many other nodes, but there is a path from one node to every other node. That's important in a strongly connected graph. So if you consider an arbitrary group of nodes, for example, if you consider B, C, and E, right? I can go from B to C, but I cannot go from C to E at all, right? And I can go from E to B, but I cannot go from B to E. So this is BCE is not a strongly connected component. BCF is a strongly connected component. ADE is a strongly connected component. The others are not strongly connected component. So this is the notion of a strongly connected component. In other words, all the members of strongly connected components can interact with each other, and there is a way of doing it. Probably they all know their phone numbers, or there are phone links, or there are roads between these houses, whatever it is possible to interact with each other. That's the notion of a strongly connected component. And that's exactly what is required here. Product recommendations based on group affiliation. Okay. So the second one I talked about was how to elect leaders, what is the vote, possibility of a voting pattern, etc. This is based on what is known as label propagation. So let us say there is a graph of this kind, and let me explain the label propagation. The labels are all the letters written inside the nodes, A, B, C, D, etc., etc. And there are also some weights attached to the edges. Please note these. Okay. So let us say we consider three nodes, A, B, and C to begin with. Now, A looks at its neighbors. So E, F, and B. The most influential number is F because the weight of the edge is 5. Okay. So A changes its label to F. Similarly, B looks at both G and D, finds that D is the most influential neighbor with a weight of 3. So B changes its label to D. Similarly, C looks at all its neighbors A, I, H, and D. The most influential neighbor is A. So it changes C, the label is changed to A. So this is the first step. Now we consider other nodes. So this was our previous result. And in this, now we are going to consider F, and then this node, and then this node, F, D, and A. The same thing repeats. F looks at its neighbors. Now, this is the most influential edge. So F remains F. There is no need to change anything. Similarly, D looks at D and it remains as D. A looks at A and A remains as A. There is no change in this particular label change does not happen in this particular set of nodes. Then the third one, now we start looking at this node, this node, this node, and this node. So E changes to F, then G changes to D, and H changes to A because of this, and then I changes to A again because of this. So finally, the labels have, all the nodes have been looked at and the labels have been propagated, and the mechanism has found 3 clusters. The nodes with the same label form a cluster, and this is a community. This is a very simple example of label propagation, and you can quickly probably note that the order in which you process the nodes may affect the clusters. We have chosen A, B, and C to begin with. Maybe if we had chosen, F and D and H to begin with, the result could have been different. So, but that is okay. As long as the clusters are formed and they have some, possibility of a cluster, we don't mind. Okay. So this is label propagation as far as this is concerned. Okay. So then the next one is connectivity analysis and path analysis. So these are very well known already. So they involve traversing graphs in a very systematic fashion. So let me underline the well known algorithms and then go to the rest. These are all well known: breadth first search, depth first search, shortest path, minimum spanning tree. These are all network flows. These are all well known algorithms. So there is nothing very special about the algorithms per se in this case. But let me give you examples. Locating neighbor nodes in a GPS system, okay, to identify nearby places of interest. So in other words, I have something here. I am standing here. This is my these are my coordinates. So I want to look at all possible, nearby places of interest. So what do? I actually look at all these in what is known as a breadth first fashion. So I look at this, and this. Then I start looking at this is level 1. At level 1, I start looking at all the possibilities, and this is at level 2. And similarly, then level 3, and so on and so forth. Why? This is because it takes a lot of time to go from here to here. Whereas these are the ones which I can reach very quickly. So that is why I am interested in very nearby places of interest, of importance that I can reach one by one after another. This is an application of breadth first search. Discovering an optimal solution path in gaming simulations. So this uses what is known as depth first search. And then finding driving directions between 2 locations, which we all do when we are driving. We use the Google map. And internally, Google will run the shortest path algorithm. Cable routing, power, water, transportation grid analysis. They all, these are all well-known examples of using minimum spanning trees and network flows. Finally, fake bank accounts and circular money transfer in financial crimes. Somebody A, B, C, D, E, F. They go on passing money from one to another. So the bank cannot find out who actually owns all this money. That is where the difficulty is. So circular money transfers can be detected only using such graph analysis. So here is an example of depth first search and breadth first search, but since I explained it already and due to shortage of time, let me go to something more important. So shortest path algorithm says, starting from the source, the shortest path to the various nodes in the system. And this is actually an example of the Dijkstra's celebrated shortest path algorithm. It is a very simple algorithm, and I am not going to explain that here. Finally, the shortest path to S, which is the source itself, is of distance 0. Shortest path to U is of distance 5. Shortest path to V is of distance 15. Even though there is an edge of 100, going like that is shorter. And then shortest path to T is of 55. So I go like this, and like this. And shortest path to W is of 73. Again, like this, I go like this, and then like this. So that would be my shortest path to W. So minimum spanning tree, if you are given a graph like this, what is the minimum number of, what are the edges which are required to keep the graph connected? So I have already shown them here. This is a tree, and these edges are sufficient to keep the graph connected. That is why it is called as a spanning tree. And the minimum amounts actually relates to the weight of these edges. So the sum of all these weights must be the minimum. There may be many spanning trees, and you can see that, right? So I can say 3, then 4, then 2, then 0, then 1. This is also another one, but this may not be of minimum weight. This one may be, this is of minimum weight. So finding minimum weight spanning trees is a well-known problem. Now let me come to a slightly bigger application. How to detect fraud and how do fraud gangs operate? Let us understand that. And we are really talking about financial frauds. So a small group of people, they share legitimate, not illegitimate. They share legitimate phone address, email, etc., etc., and they create a number of fake identities. So if there are 2 real addresses, 2 real phone numbers, and 2 real email addresses, right? So now I can create 8 of these fake identities. I can group like this, right? All these are possible. So I can create a large number of them. Some of them may not be very good, so I eliminate. But maximum I can create up to 8 fake identities from these. Some of them may not be good, some of them may be useful. They open bank accounts with these fake identities, and then they obtain credit cards, loans, overdrafts, etc. They operate the accounts normally for some time. They are very good citizens. Then what happens? The banks increase the credit, loan, overdraft limits. And finally, one fine day, all the members of the gang utilize maximum amounts in these facilities, and they disappear together. And since they're all fake identities, banks can never trace the gang members. Even if they go to that particular address, which is a real address, the person there will say, I don't know, somebody has misused my address. So this is the modus operandi of a fake gang. How do we find such fake gangs? So detecting fraud rings and stopping them from causing damage is a very hard problem. Traditional methods do not use relations. They do not use graphs. They just use deviation from the normal usage, which doesn't exist here. Whereas graphs can show explicitly, they show rings explicitly, and detecting them is easy. Let me show you an example now. So here is account holder 1, account holder 2, account holder 3. So now this address is shared by all the three holders, but these accounts may be in different banks. So they have no idea that they are sharing the address and all that. So whereas these people, they share the phone number, right? And then these two share the social security number. In our case, it will be the Aadhaar number. But once a graph of this kind is created, it's easy to see that account holder 1, 2, and 3 share a lot of these pieces of information. These are the rings that we are talking about. So once a graph is created, fake identity rings are very easily detected. The same thing happens in online transactions. These are the IP addresses. These are the credit card numbers. These are the IDs of people. And these are the cookies. So a single IP address is actually operating 4 credit cards, 5 credit cards, right? 5 credit cards. And a single credit card is operated by so many people also. So when a graph is created, it is possible to know all this information. That okay, a single IP address is using so many credit cards, a single credit card is used by so many people, etc., etc. And possibly the fraud investigators can investigate and see whether things are going correctly. Okay, so that is about a large, application that is possible. Now let me tell you a little bit about the requirement for a distributed graph analytic system. So processing very large scale graphs requires distributed systems. There are applications to social networks, Facebook, Twitter, road networks, systems biology, web graphs, etc., etc. Let me show you some sizes, typical sizes. These are some, graphs that we use in practice to test out our applications. So V is the number of nodes and E is the number of edges. So you can see here 100 million, 200 million, right? So this is 39 million. This is 1 billion and 41 million, etc., etc. Here there are 3 billion edges, 1 billion edges, 100,000 million edges, etc., etc., etc. So the problem is such huge graphs cannot be stored or processed on a single machine. Just not possible. What it requires is distributed execution. Okay. So basically, we divide the graphs into many parts. I am just showing you 2 of them here. Part 1 is resident on one machine. Part 2 is resident on another machine. And these edges are all between these machines. Okay, the graph pieces of graphs are here on different machines, and in between are known as the partition edges. So the algorithms that I gave you examples of all these minimum spanning tree, distance, shortest distance, etc., etc., between the centrality, they will have to actually operate in this partitioned manner. That is where the difficulty is. There are further difficulties. Graph algorithms, they have a lot of parallelism in general, but they have very bad irregular behavior. So there are random memory access patterns. It may, this example shows you already. This may be on one machine, and suddenly it requires to look at node B, which is not on the machine at all. It could be somewhere else. The speed up depends on the graph structure and how it is partitioned. Graph topology can change over time. There may be websites added or removed over time. And you require a different data structure for each type of hardware and the algorithm. This is a specialty of the implementation. So all this makes it extremely hard to exploit the available parallelism in a graph algorithm. And programming them directly, like in CUDA or MPI, OpenMP, it's like writing assembly language programs. That is where the difficulty is. So we come to the notion of a heterogeneous distributed system. There are multiple cores, and then there are GPUs. GPUs themselves have a very large number of cores, And distributed systems, they contain multiple GPUs, multiple CPUs, and a GPU cluster also, and clusters of these machines in general. So they have a very fast interconnection network. They are programmed using what is known as an MPI library, and data distribution, synchronization, etc. have to be taken care of by the programmer. In other words, these systems are very powerful, but exploiting them requires an intricate knowledge of the entire system, the hardware, the software, and programming is more like very low level. It must be done with OpenMP, with C++ level, with CUDA, and so on and so forth. Very assembly level sort of programming is necessary. So a single program does not suffice for both CPU and GPU. They require different types of separate programs. And then the programmers must know all the details, as I already told you. Then there is graph partitioning. Then you have lots of parallel threads running, so thread management is needed. Then you have memory for graph objects, copying graphs from one machine to another machine, etc., etc. Then you have to pass messages between machines. Then, of course, global variables is always an issue, and debugging such programs is horrendous job. So a possible solution is to use a high-level domain-specific language for programming graph algorithms. And there are also several known models of parallel programming, which I am not going to discuss. And one of the most famous is the bulk synchronous parallel model, which was proposed by Valiant, who is one of the Turing Award winners. And now the compiler takes care of all aspects of graph partitioning, thread management, memory management, global variable management, etc. And the compiler should be able to use different partitioning strategies and optimizations. So one simple example is our language, which we call as Falcon. Is a domain-specific language for distributed graph processing. It is based on C. It supports shared memory, and then it has a graph data point, this data structure, point data structure, edge data structure, set data structure, collection. All these are available to the programmer as high-level data structures. There is parallelism possible, so parallel iterators are available. Synchronization is possible, and compiler handles all aspects of thread, memory, and message passing. And of course, whether we are using a single CPU or a single GPU or a combination of these two, the compiler takes care of generating code appropriately. Here is a very simple example of the shortest path algorithm. I don't want to run through the program per se, but it suffices to say that it has a graph data type. It has a facility to read a graph completely, and then it has a parallel for loop possible. So they process all the nodes in the graph at the same time. Okay, so these are some of the highlights of a simple program for in graph in Falcon. So there are many others available in the literature: Galva, Greenwald, Totem, Lone Star, Totem, etc., etc. Power graph. They're all very good. They are meant for different purposes. So of course, I have to say that Falcon was built after all these came into existence. So it has taken care of some of the shortcomings of this. So that brings me to the end of my lecture, the future. So graph analytics helps in social network analysis, fraud detection, and many other applications. So graph processing languages, graph database bases, and graph analytics frameworks will be essential in the future. And graph analytics can be combined with machine learning to improve the accuracy of ML applications. So, and finally, bit of advertising. This is our brand new book, which was published in May 2020 by Springer on distributed graph analytics, programming languages, and their compilation. Thank you very much. And of course, Unnikrishnan was my PhD student who was actually the inventor of Falcon. And Rupesh Nasre is an assistant professor, now an associate professor in IIT Madras. So both were from IISc. Unni Krishnan was my student, and Rupesh Nasre was Professor Govindrajan's student in IIS. Thank you. I can take questions now.
Thank you so much, sir. We are spellbound. The interpretation of graphs to day-to-day applications was so exciting. The research language used was so simple to explain concepts. Sir, you have inspired many to take up graph theory for CS applications. That was very gratifying experience, sir. Thank you so much. Now I'll just go to the chat box and read out the questions. And
Yes.
you please, if you have questions, please immediately post it here. Sir, one question that we have is, yes, give me 1 second, sir. The degree of centrality or in degree and out degree alone important, or should we consider the quality and importance of the adjoining node also?
See, that depends on the algorithm. So degree centrality is one of the measures, right, which considers only the degree. So closeness centrality and betweenness centrality consider the shortest paths. Okay. So the label propagation algorithm looks at the different nodes, the weights between the edges, etc. So the answer is a single centrality measure or a single community detection algorithm does not suffice for every application. There is nothing like the best. Every application has to be analyzed to see what kind of centrality measure or community detection it requires, and then the algorithm must be applied. So in short, yes, it is important to look at the adjoint neighbors and all that, even the weights on the edges. Just the degree will not be sufficient.
Sure, sir. Thank you, sir. There is a question by Anil. For real-time graph analytic applications in dynamic graphs, how is distributed storage and execution done?
So repeat the question.
For real-time graph analytics applications in dynamic graphs,
Yes.
how is distributed storage and execution done?
Okay. See, first of all, let me answer it in two parts. First is the dynamic graph. So I understand dynamism would be the graph is going to change in real time. So in fact, for that, for such a class of graphs, very efficient graph algorithms for all types of applications do not exist today. So one possibility would be to compute all the properties all over again. If the graph, let us say 100 edges are removed and a few are added, the graph has changed. Now, shortest distances will change. Whether we can use the previous shortest distance information and compute the shortest distance information for the new graph, it's very difficult to say, because we can compute everything all over again, but it takes time. So there are dynamic graph algorithms for only a very small number of applications. That is one part of the answer. Second, graphs are partitioned. So within the partition, there may be edges and nodes which are deleted. And now if the partition itself becomes very, very small, it is likely that this causes some kind of an imbalance. So there may be a need for repartitioning of the graph itself, but that is a very large exercise and usually not undertaken. So the two are different. Dynamic graphs and algorithms, the partitioning and distributed execution. These two are two different things. Yes, they can be handled, but for dynamic graphs, the technology has not arrived, in my opinion.
Thank you so much, sir. There is a question. I suppose Falcon is not object-oriented. Any particular reason why it is not?
So in other words,
yes,
yeah.
sir.
Please go ahead.
In terms of applications, are they more CPU intensive or memory intensive?
See, Falcon is C-based. For the reason is the objects that we desire are already built in. For example, graphs are the objects that we want. We wanted to do only graph processing. Most of the domain-specific languages are not supposed to do very general purpose computing. They are not supposed to be used for such applications. So when we are doing graph processing, our main objects are graphs, edges, points, etc., etc. And these are already objects available in this system. That is one. Second, making it general purpose object oriented actually causes inefficiency. So object management comes into picture, whereas C is an extremely simple language to compile and all that. Efficiency is very high. These are the reasons quite a few of the existing graph processing languages, they are based on simple features of this kind. They are meant for graph processing only. So that's the point.
Sure. Thank you so much, sir. There is a simple generic question: can fraud be avoided? I don't know what is the background behind this question.
See, fraud is human nature.
Yes, sir.
So as long as humans exist, there is nothing like, you cannot make every person a good boy or a good girl. It's impossible. The dynamics of a society are such that everything, it has been in existence right from the day Earth and human beings came into existence.
Yes.
So obviously frauds cannot be avoided. If we see, the people came up with viruses, then there were antiviruses, right? So, and we now have frauds. So we came up with fraud detection. The people actually said encryption is the end of everything. No, there are efforts to break the encryption. So for every technique that we envisage, there will always be an effort to break the technique, and fraud is human nature. There's nothing we can do about it.
Yes, sir. Lastly, it's not a question. There is a request from Mr. Hemant YK. It's very exciting to have a 5-day workshop on this topic alone. It will be extremely useful. That's observation by Hemant.
Well, that's it's possible if
Yes.
people arrange different types of lectures on graph analytics. It becomes very intensive. See, I'm going to teach a course on graph analytics in our institute next term under the Proficiency program. But it is actually an advanced course. In other words, people must already have a degree in computer science. They must have gone through a course on data structures, algorithms, some parallel algorithms. Unless there is exposure of that kind, bringing everybody to speed in graph analytics takes a much longer time. 5 days is just going to give an introduction. If an introductory set of lectures is what is desired, then possible. Yes, definitely it is possible. People can organize it, arrange lectures by various eminent speakers, and it is possible. But hands-on experience will be very, very difficult. That is because what I said, people need a lot of background before they start programming with such graphs.
Thank you so much, sir. It was very revelating. I hand over to our Honorable Vice Chancellor, Professor K.M.P. Murthy, for his vote of thanks.
Good morning. I take this opportunity to thank the speaker of the day, Professor SRIKANT. He agreed to deliver this lecture, and I'm sure each one of us have benefited even with no background and graph or graph analytics or whatever. He made it so simple. He ensured that the entire topic or the complex concepts are being explained through real life examples. I think that's the standard feature of this particular thing. On behalf of Bytes and Dayanand Sagar University, I think I need to thank Dayanand Sagar University for willingly agreeing to host all the lectures, providing all this technical support for hosting such lectures. And a lot of students stand to be benefited from this lecture. More than 500 students and faculty attend this lecture, both through YouTube and the Zoom. Zoom had a limitation of 300. It was full. Then we had to open a YouTube live. I'm sure the students have benefited from this lecture. And there's also a request from all of them that more lectures can be organized. If Professor Y.N. SRIKANT is ready, probably Bytes would come to him with another request for one more lecture on graph analytics and possibly one or two specific examples in a larger depth. I'm sure the lecture was so generic to reach out to all the people. And I thank Mr. Imtiaz for providing all the help to us, and the organizers of DSU, Professor Srinivas and his team for providing, and also thank Professor Vital Rao and others who are present in this lecture. I think they attended this lecture. Professor Vital Rao was is a regular attendee for our Bytes lectures, and his lectures were well appreciated. And I'm sure these lectures would give lot of insights for students to plan out and try out few projects and solving few problems to get the expertise. I think it's more an enjoyment of working on these kinds of topics. And Professor SRIKANT has made it so simple. Sir, thank you very much, and we'll come back to you with more requests in the future. Thank you very much.
So thank you, Professor Murthy, Professor Srinivas, and everybody else. It was an honor for me to deliver this lecture, especially with my guru, Professor Vital Rao, in the audience. I hope I have been able to achieve at least 1/10 of the quality that Professor Vital Rao actually brings to his lectures. Thank you very much. I look forward to interactions of this kind again.
Yes, sir.
Okay, bye-bye.
Vital Rao, sir, are you there? You have the access? Audio?
Yes, sir.
Yeah, you want to say? Yeah.
1/10 is to be multiplied by 1,000. Yes. Anyway, it was really fantastic. Of course, I am not a computer science man, but still I was able to follow most of what Professor SRIKANT said. And well, there are one or two things about the page rank, which I will discuss with him personally. I think that factor 0.85, Professor SRIKANT.
Yeah.
That was some kind of what we call a jugad. Because if he had put all one there and he had not added the other term, there would be matrix problem. He would not have got a positive rank vector. Therefore, he had to add one term there to make that matrix irreducible. And so that 0.85 itself was a random factor. It could be 0.95 also.
Yeah. That's right. I think it was more empirical. Yes.
Yeah, it was more empirical, and he had to do it. He called it teleporting or whatever it is. But it is, I think, without that, the whole thing would have collapsed.
Correct. You're right.
Yeah, right. But anyway, fantastic lecture. Thank you very much.
Thank you.
Thank you, sir. Thank you.
Okay.
Again, we'll meet again on the 18th of this month for a lecture by Dr. P.G. Divakar from ISRO. That will be on Bhuvan Geoportal and the real-time tools of related tools on Geoportal. There's a lot of projects and other things will be discussed on the Indian satellites, the kind of data that we get. It's on 18th. We'll come back to you on 18th. Thank you. Thank you very much.
Okay. Thank you. I will disconnect now. Thank you.
Yes, sir.